Okay, so we're going to continue today talking about cosmology. I didn't get as far as I hoped last time, so I might have to pick up the pace a little bit. But I did want to at least lay the groundwork for the rest of the lectures. So we're going to talk about large-scale structure to start, which was the second part of the first lecture. And then we're going to move into the CMB and N-effective as planned. So last time I sketched you the picture of the power spectrum of matter in the low redshift universe. But I just wanted to first think about what's going to happen over time. So we have this picture. We have something like the time of recombination where we had this like hot and cold spots. And the fluctuations in the temperature during this era are about 10 to the minus 5. Okay, and then on this axis, time evolves forward. And somewhere here we have galaxies. Okay, so we have nice, big-looking things filling the universe. And these are definitely nonlinear objects. So in order to create galaxies, we better have density fluctuations that are bigger than 1. Okay, so hopefully that's not a controversial statement, but a galaxy is definitely a nonlinear object. This is definitely a very small fluctuation. And so we presume that something happened in here, presumably gravitational collapse, that took us from the CMB to our galaxies. Okay, that seems intuitive. It doesn't seem particularly dramatic. And of course, that same fairly intuitive and not very dramatic thing is what people thought 50 years ago when they first started worrying about measuring the CMB. But they came up with the following argument. Okay, so if you want to think about this process, the first thing you have to do is figure out how quickly do things collapse. So what is the gravitational collapse actually doing? So I won't go, it's in the notes, this is derived in detail, but roughly speaking, okay, so these are small fluctuations. We can start by just asking how quickly the small fluctuations grow before we worry about anything nonlinear. So if we just do linear gravity, and here we're even just going to do linear Newtonian gravity, because that's a good enough approximation, we can ask ourselves how quickly do the fluctuations grow? Do they grow? When do they start becoming order 1? So you say, so the equations that describe Newtonian gravity are mass conservation, momentum conservation, and the equation for the gravitational potential. So mass conservation looks something like this. I'll write it in terms of the density contrast. So I'll work with density contrasts that are defined this way, the change to the density over the density. And so the first thing is we have mass conservation, which tells us that the change in the density is related to the divergence of particles out of the region. Okay, so the way you change the density over time is by having stuff move. Okay, the second equation is determined by momentum conservation. There is a factor of a factor of Hubble here, just because of Hubble damping, so or Hubble friction, if you like. You know, the velocities redshift away. So if nothing happens, there's no forces, the velocities are going to go to 0. But there's gravity. Gravity pulls on stuff. And so, of course, we have the divergence of the Newtonian gravitational potential. And then we remember that all physical length scales have to have a's in them. And so I have to divide this by a factor of a of t. Then we have the last equation, which is the Poisson equation, which I'll write this way, where this is, again, the density contrast. And again, I remember that I need to divide by a squared because these are physical quantities. Okay, so derivatives are like 1 over x. Physical distances are a times x. Okay. If you take a matter-dominated universe, which is true starting back here. So in our picture, matter domination starts at z of approximately 3,000, which is 3 times higher redshift than the redshift of recombination. Okay, so we're living in a matter-dominated universe. In a matter-dominated universe, So here, I'll raise this a little bit. So h squared, we'll write the Friedmann equation is given by the energy density. So the energy density of matter, so if this is matter, this is like a to the minus 3. So that tells us that if this h goes like a to the minus 3, which tells us that the Laplacian of phi goes like 1 over a times the density contrast. Okay, so from those things we learn the following. So we learn that phi is like 1 over a with, so let's write it this way, k squared times phi is like 1 over a times delta in matter domination. Now, if you plug all those things back in and you solve this equation, you'll find that delta goes like a to the plus 1 plus a to the minus 3 halves with some constants, c1, c2. And so as a grows, the universe gets bigger. We can ignore this term. And that tells us that phi is actually a constant. And the density is growing like the scale factor. Yeah?
Around the time of matter radiation quality, how careful do you have to be with your scale factor?
Well, the scale factors always come with distances, but there's lots of other factors. There's actually, the thing when there's radiation is relativistic, and so you have to worry about treating gravity relativistic as well, and so there's different derivatives of the potential. So the real thing that I did wrong was to just treat gravity as Newtonian in that case. Okay, so, yep. Oh, just this. Imagine they were equal at recombination. Then this thing grows by a factor of 1,000, and this thing falls away like a factor. So eventually, it doesn't matter. So for the purpose of stuff becoming big and nonlinear, I only have to worry about the first term. Okay? Okay, so with that, we remember that redshift and A are inversely related. So the redshift of recombination, Z star, was equal to 1100, which told us that A at the time of recombination was about 10 to the minus 3. So if something grew linearly from recombination until today, that means it grew by a factor of 3. So if delta was equal to 10 to the minus 5 at T star, then delta would be 10 to the minus 2 today. Okay, you should be deeply troubled by this because that's not big enough to form nonlinear structures. And this isn't a dumb mistake. This is why people were really worried when they didn't measure the temperature fluctuations of the CMB at 10 to the minus 3. Because if you invert this argument and you've never measured delta T over T, you'd say, well, I definitely know I live in a nonlinear universe, and so delta T over T better not be smaller than 10 to the minus 3. But it is. I mean, we've measured it. It's much smaller. So what did I miss? What's wrong with this argument? Nonlinear effects are small because it's 10 to the minus 2. So nonlinear effects are down by a power of 100. So I'm going to give you a hint. What were people maybe not sure existed like 50 years ago that now we really think exists? Dark matter. Okay, so why might dark matter change this story? Does anyone have any guesses? Is that so? So the same as I could have put any kind of matter, including dark matter, in this expression. Okay, so what's different about dark matter from? So I put delta T over T there. Yeah.
Since it wasn't coupled to the plasma before this all happened before.
Yeah, so that's correct. So we see delta T over T. That's a measurement of the density fluctuations in baryons and the density fluctuations in photons, not the density fluctuations in dark matter. So what we immediately conclude is that at recombination, delta rho over rho of the dark matter was bigger than delta T over T. The dark matter, somewhere, some of the fluctuations in dark matter had to have actually been bigger. Okay? Now, we can think about what's going on in the following way. So here, to understand, this immediately implies something interesting. So the answer is really that the things start growing linearly when they cross the horizon. So horizon crossing is defined by the time when physical, so we're going to call this horizon crossing, okay? So this is going to be called horizon crossing for the purposes of all these lectures, okay? So this is the time when a given Fourier mode's wavelength is the same size as the curvature of the universe, or when its wave number, or roughly frequency, is the same as the other time scale in the problem, the expansion rate, okay? So this is an important scale in the problem. This is what tells us the difference between things looking like they're Newtonian and things caring about general relativity. So things on this scale care about general relativity, but then they come inside the horizon, and then they behave kind of like small scale fluctuations. So what matters, so things start growing like A of t when they cross the horizon in matter domination. So the first thing we learn is that the modes that would have had longer to grow are the modes with higher k, because they crossed earlier. Now I'm skipping one step here. I should just remind you, remember, h goes like 1 over a squared. So even though this is getting smaller, h is getting smaller faster. So this equation, k equals a h, goes like 1 over a. So as time goes on, smaller wave numbers come inside the horizon. So the bigger the wave number, the smaller the value of a when it crosses the horizon, the earlier in time. So the things that had the longest to grow, the things that have been growing for the longest, have bigger k. So larger k is the same as growing for longer. So the nonlinear modes must be the small scale fluctuations. So the modes, the fluctuations in the dark matter that are the ones that have gone nonlinear, must be the ones that have the biggest k, that had the longest time for us to see them. Now, if you remember the picture of the CMB has no power in small scales. So the CMB looks something like this, and it's going exponentially to 0 here. This is because of dissipation of the sound waves. The sound waves, you yell and the sound goes away. It doesn't bounce around the room forever. The same is true here. The sound waves go away. So in this part of the picture, delta t over t is getting really small. It's actually much less than that 10 to the minus 5 that we like to quote. And meanwhile, the dark matter must be doing something like this. The dark matter must be growing, okay? It must live somewhere in this picture where we're not seeing anything because the sound waves are going away, but secretly in the dark, these dark matter fluctuations have been growing for a long time, and that's the thing that's going nonlinear. Okay, so that's the first thing. The second thing is that this was the story in matter during the matter era. So in the radiation era, the story is slightly different. So in the radiation era, the equations for the mass and momentum conservation of the dark matter are the same. But now the equation, roughly speaking, I'm just going to put this here, is this equation is still the same. Oops. Where this is now, these are now the fluctuations of the photon baryon fluid because they dominate the universe. And h goes like 1 over a to the 4th because of radiation. I think I screwed that up on the other board. But so now in this case, the photons are not growing, right? We see the plot. They're not growing. So this thing is not getting bigger. This is going like 1 over a. This thing is going like 1 over a to the 4th. Then that means that phi is going to 0, or going like 1 over a squared to 0. So gravity is not doing much to grow the density fluctuations. And so you can go back to this equation, basically set this term to 0, and you'll find that you basically get at most logarithmic growth. So during the radiation era, they're not growing like the scale factor. The metric fluctuations are going like log of time. Let's write like this. So if we put back our factors of k so that we always put k's and a's together, it will look like this, or k over a like that. And this is where the picture comes from. So when we plotted the matter-power spectrum, you'll see a picture that looks like this. Here, this is linear in k. The region here, so at k much less than k equality, which is the mode that crosses the horizon, the modes that cross the horizon when matter and radiation are equal, that's just the constant potential. So the potential is constant. So the matter-power spectrum is just k to the fourth times our constant potential, our constant fluctuations of the metric. And so because this thing, which we have yet to explain from inflation, goes like 1 over k cubed, this gives you k. Over here, this part is going like log k squared divided by k cubed. And the difference between these two things is the difference between the way it grows during matter domination and the way it grows during radiation domination. Yep? Oh, that was just a t. That's just the growth. It grows logarithmically in time. So this is the picture of what's going on. Now, we can translate this into which modes go nonlinear by plotting not p of k, but k cubed times p of k. So if you remember, we take a Fourier, we care about this being order 1, the one in position space. And remember, Fourier transforms just give you 1 over k cubes by dimensions. So this is, roughly speaking, like this quantity is kind of the same as the variance of a given Fourier mode on a given length scale. Does that make sense to people? There's 3 powers of k that come from doing a Fourier transform that have no important significance. So we're just putting them back into p of k to ask how big is the characteristic fluctuation in the appropriate dimensionless units, not the units with just funny k's in them. Does that make sense? OK, so now let's think about what this plot would look like in a universe with dark matter, so the one we inhabit, compared to the one without dark matter. So k cubed p of k will look like k to the fourth in our universe, and then grow like a log. I didn't use my space very wisely. Here, let's do this. OK, so it grows like k to the fourth, and then it grows like log squared, and then somewhere in here is 1, OK? So somewhere in here is 1, and this corresponds to, we'll just call this the nonlinear scale, OK? For people who like units, it's about 0.1 h inverse megaparsecs. That won't mean anything to most of you, but this is about where it crosses 1. This is where things become nonlinear. So over here is nonlinear. Now, if we had lived in a universe with only baryons and no dark matter, the picture would look something like this. It would be smaller to start because it wouldn't have been growing from matter radiation equality. It would have been growing from recombination, which is later, has less time to grow. It'll follow k for a while. Sorry, it'll follow k. So here was the bend. This was equality. Sorry. It'll go a little bit past the bend, but then it will just have big oscillations because they're baryons. Okay, and this was our problem with baryons, is that they don't grow when they're sound waves. They just oscillate. And the whole picture will go up after they decouple from the photons, but as we saw, there wasn't enough time for the whole picture to go up. Now, what this means for the matter-power spectrum is that if you were to plot the nonlinear matter-power spectrum on top of this, it would look something like this. So this is the nonlinear part. And this white one is the linear one. But the takeaway here is that nonlinearities are all happening on small scales. Yeah, do you have a question?
Yeah, thanks. How much could you change this picture by putting in non-zero curvature?
I haven't thought about it. I don't have a good answer. Okay, so the key here, though, is that this isn't just some totally random fact, right? So many of you have probably seen this plot. Who's seen this plot before? Including the nonlinear one. Who's seen the one with the nonlinear line? Okay. Who here has thought, this nonlinear is on the right-hand side of the plot because dark matter exists in the universe? Okay. So now you all know. Now you remember. When you see this plot, that's dark matter. That's what it's doing. This exists like this because the short modes are the ones that had enough time to grow to become nonlinear. The long ones didn't get to grow. They can't become big enough. And that's why you don't have nonlinear structure formation. So again, everything about this plot should tell you there's no doubt in your mind that dark matter exists. And so anytime someone tells you that MOND is a really great idea and we should take it more seriously, you can tell them about this plot. Yep.
What do you mean by nonlinear?
Oh, sorry. Non-linear here means I've completely ignored any effect that goes like delta squared, and I've set them all to 0. So I'm treating only linear perturbations.
But at the k equality, the amplitude is big, right?
Not on this plot, right? The correct way to measure the amplitude is k cubed times power spectrum. So at equality, remember, k cubed keeps growing. So again, remember, this plot doesn't mean what, because these numbers, if you go and look, this number is like 10 to the 5 or something like this. This number is not, you shouldn't measure 1 as being the definition of linear nonlinear. So
P is defined as a delta squared, not k cubed.
no, it's defined as delta of k squared. And delta of k squared is not dimensionless, right? It has units of 1 over k to the 6th. So if you want to tell me what is the meaning of that, I have to convert it to a dimensionless number. So that one is the dimensionless quantity. Yeah.
Actually, delta is going to, one is, we cannot use the perturbation, but we still can talk about slightly about the nonlinear.
So somewhere in here you can use perturbation. So somewhere in here is quasi-linear. And this is where nonlinear perturbation theory lives. And then this is simulations. But the orange curve you'll see, well, actually, most of the time the orange curve you see is like some fit to data called the halo fit. But like, you can do the one from simulations, and it looks something like this.
One more is that why it's just pass through us slightly, not oscillates line away.
Sorry, what was that?
So why it still pass through?
Because of the log. So it's really like it's the log squared.
I mean, for the partial cases, why it doesn't oscillate right after?
So so our argument before had to do with the fact that sound waves don't grow, right? Sound waves don't grow at all. They don't even grow like log. They just oscillate up and down. And actually they go away, right? So I should have put damping in here. They go back down because the sound waves dissipate, the same way the temperature does.
What is the horizontal axis?
What's the horizontal axis?
Time or?
This is K. This is higher K. Sorry, I'm going to stop using the yellow chalk. It's lost its purpose. But okay. So this is K. This is just the power spectrum multiplied by K cubed, because this is dimensionless. So when I compare this number to 1, it means something. Yep.
Maybe this is not a meaningful question even to ask, but if you're saying that the large length modes, the small K modes have not had much time to grow, and so you shouldn't see nonlinear effects. Is there a time we can predict that we could see nonlinear effects in the future?
They will not, because we live in an dark energy dominated universe now. Now nothing grows. Nothing. We're going to all be separated from everyone else, and we'll be sad and lonely people. But then we'll die from radiation death, and then we won't care. Yay. So yes, but yes, that's yeah. That in principle, this is a thing. If we were in a flat universe, we could have discussed. Okay, is this picture clear? Yeah.
I just missed what you're trying to do on this board.
Okay.
I get that, like, the smaller or larger wave numbers are going to run 10 times rise in local harm. I didn't understand what that had to do with the dark matter story.
Oh, because this only applies to the dark matter. Because the sound waves, they're not growing because they're bouncing into photons. The photons are pushing them apart. Photons are keeping any matter from growing until they decouple at recombination. So recombination, so this picture is totally applicable to the baryons. This is what the baryons do. The baryons are too small, their fluctuations, to become nonlinear. So baryon fluctuations are basically linear. It's entirely, except for the fact they couple to dark matter, which is nonlinear. But it's the fact that this only applies to the dark matter because they start growing when they cross the horizon because they're not talking to the photons.
Just so I understand, so the reason we're making this distinction between linear and nonlinear growth, when we looked at the linear growth, this was when we found out that we couldn't reach the sufficient overdensities for galaxies. Is that?
So linear growth is completely applicable as long as the density fluctuations are small. Once they become big, then you have to include nonlinear effects. So here, without appealing to nonlinear effects, we already knew they were not big enough to become nonlinear. So we were safely ignoring. So this is just like a perturbation theory argument. This was completely consistent perturbatively. This one will break down perturbatively for high K. And that's what we need to make galaxies and things that don't come out of perturbation theory. Okay, any more questions? Okay, so this will allow us to move on to the beginning of lecture 2. So hopefully we can try to catch up. But all right, so now we're going to go back to the CMB, and we're going to talk about ineffective. Okay, so the goal of these lectures, this second topic is ineffective. Ineffective is synonymous with sometimes called dark radiation. We know that at different periods in the history of the universe, dark matter dominated and dark energy dominated. And so if you are religious, then you might think that we need a holy trinity, including dark radiation. And so it's natural to think maybe this exists and that we should go and look for it. Okay, so to understand what dark radiation might look like, we should start with the kind of dark radiation that actually exists in the standard model, which is neutrinos. So neutrinos are effectively a kind of dark radiation in the standard model. They don't couple to the photons or baryons at late enough time. So from the purpose of a cosmologist, this is invisible. It doesn't couple to light. It has an abundance that we'll talk about in a second. And so how we think about the search for cosmic neutrinos is in one-to-one correspondence with how we would think about searching for any other new light particle that behaves like radiation for some part of the history of the universe. Okay, so I'm going to pause here to ask a question. Did Ben Safdie talk about the neutrino temperature or the axion contribution to ineffective in his lectures? No, no one saw this? Okay, that's fine. I'll go over it. I saw earlier version of the notes where he did, and so I didn't want to waste time if he didn't. Okay, so the first thing we're going to do is we're going to talk about the cosmic neutrino background. Okay, so neutrinos couple to the standard model through the weak interaction. Okay, so they scatter. So you can take, say, like you can convert electrons into neutrinos through the effective G Fermi interaction, the 4 Fermi interaction. So this cross section, just on dimensional grounds, we can convert the rate at which we produce neutrinos. So we produce neutrinos that goes like G Fermi squared, because that's the amplitude. And then this is a rate. So this is the rate of production. And so a rate is like 1 over time. The only other thing in the problem is temperature. This has units of 1 over energy, so it better be temperature to the 5th. Okay, I'm going to do all twiddles because putting 2's actually has no useful value. You'll get everything right without using 2's. Okay, so this is the rate at which we produce neutrinos. Now, this is enough as long as this will be effective at keeping neutrinos in equilibrium if this is greater than the Hubble rate at that same temperature. And now, at high temperatures, the universe is dominated by radiation. And so the Hubble rate is set by T squared, some factors of the number of degrees of freedom in the standard model, and I think there's a pi squared over 90, and then an M Planck, okay? So the Hubble expansion rate is like T squared over M Planck. The production rate is like G Fermi times T to the 5th. So when T is really big, this is obviously going to win over T squared. Opposite is true. T is very small. This thing is going to become unimportant. The expansion is going to win. And then once expansion wins, you just have dilution of neutrinos. They're not being produced anymore. They're just diluting with the expansion of the universe. OK, so if you just estimate this rate, that the place where this crossover happens, let's see, do I have? OK, so if you estimate where this happens, it happens when gamma is approximately equal to h. Okay, so that's roughly speaking when the temperature cubed is approximately the mass of the W to the 4th divided by M Planck. And this is about 1 MeV cubed. Okay, so the actual, if you do these things in detail, like the number is maybe 2 to 10, like it kind of starts decoupling from the standard model somewhere between 1 and 10 MeV. The only critical thing is that this number is 1 MeV or slightly bigger. That will be important in 1 second. Okay, so this we're going to call, we'll call this the freeze-out temperature for neutrinos. We'll put a little u here. So remember, it's where the neutrinos freeze out. So I'm going to use TF to refer to the temperature when some particle went from being in equilibrium with the standard model to not being in equilibrium with the standard model. Okay, so after decoupling, the neutrinos just continue to follow the expansion of the universe. They still look like they're in a thermal distribution because now nothing's changing. So whatever distribution they were in, they just stay in that distribution. The only thing that happens is that everything redshifts. So all physical length scales just go like 1 over A. And so what happens to the neutrinos is that they're very boring, and nothing else happens to them for a while. And so their temperature just goes like 1 over A. So the neutrinos' temperature is just equal to whatever it was at the decoupling times 1 over A. Whatever moment they decoupled from the standard model times 1 over A. Now, for a little while, the same is true for the temperature of the photons or the standard model. So for a while, this goes like 1 over A as well. Okay? But does anyone know what happens after decoupling that changes the story? Yeah, so, well, electrons don't decouple. So the key fact is that 1 MeV is greater than the electron mass. So electrons were in equilibrium. So at this time, there were photons, electrons, and positrons around in the universe. But at some point, the temperature drops much less than the mass of the electrons, and then there's just photons left. Now, the key issue, though, is that entropy is conserved in the universe. So entropy is conserved, which basically means that A cubed times T cubed has to be is a constant, or A cubed times the number of degrees of freedom is a constant. Okay, so this entropy, there was entropy stored in these E plus E minus pairs. That entropy went somewhere, and it basically has to go into photons. So it has to heat up the photons, increase their temperature, so that the photons are no longer following the 1 over A. Nothing interesting happens to the neutrino temperature, but since we know the temperature of the photons at recombination, we interpret it as changing the relative temperature of the neutrinos, but it's really the photon temperature that changes from annihilating electrons and positrons. Okay, so we can use that to calculate the temperature of the neutrinos. So all we have to do is we have to calculate this entropy and make sure that it's equal at the 2 times. So let's start before decoupling. So before neutrino decoupling, so in this case, we have, so let's remember that G star is equal to the number of bosons plus degrees of freedom times 7/8 times the number of fermionic degrees of freedom. This is the G star of a gas of particles made of fermions and bosons. Okay, so let me say, I'll say relativistic particles. So I'm just going to count the relativistic ones. Okay, so before neutrino decoupling, the entropy, and I'm going to drop a factor of pi squared over 45, is the number of degrees of freedom in photons plus 7/8 times the number of degrees in neutrinos plus the number of degrees in electrons plus the number of degrees of freedom in positrons times whatever the collective temperature is, and I'm going to call that nu, because at this time everything has the same temperature. It's the temperature of neutrinos at this specific time, so we'll call this T1, times whatever the scale factor is at this initial time. Okay, so that's before. Here, maybe I'll do it on another board so we can compare. Okay, so now we're going to do after. So now we're going to wait until after the electrons and positrons have annihilated. It doesn't matter, this is a constant, so we can choose whatever time we want. So now we're going to do T much less than M electron. And so at this time, we're going to call T2, so we're going to call this time 2. S at time 2 is equal to, well, now there's the temperature in photons times A cubed at T2 times the number of degrees of freedom of the photons plus 7/8 times the number of degrees of freedom in neutrinos times the neutrino temperature cubed times A cubed at T2. Okay, so any questions about the 2 entropies so far? Yeah.
It's only TQ, it's not T to the fourth.
T to the fourth, sorry, T to the fourth is the energy density. This is entropy. Okay. So, which is basically P, it's roughly rho plus P divided by T. So that's the missing 1 over T. Okay, now we just want to equate these things and solve for T gamma. Notice that I have not made T gamma the same as neutrino temperature. Okay, so now we just say S of T1 is equal to S of T2. Now, it's important that T nu times A is a constant, right? As we said, nothing interesting is happening to the neutrino temperature, so this part doesn't change. So T nu times A at the second time is the same as at the first time. And so we'll see that this factor completely cancels against this factor. It's the same on both sides. So if we write this out, we have we'll just put this factor in so we can see it cancel. And then that's equal to and then we had this extra factor that I stripped off. Okay, so these cancel. So the fact that there were neutrino degrees of freedom around actually didn't matter at all. all the action was happening, as you might expect, in the number of degrees of freedom in the electrons and positrons compared to the number of degrees of freedom in photons. Yep.
Perhaps it should be obvious to me. Why are we sure that the entropy should be conserved across decoupling?
Because so the entropy, there's no process that's creating entropy there. Like we're just, I'm trying to think of the right words. So that like entropy is conserved in thermal equilibrium. So the key thing that's happening is that for our purposes, we actually don't care about what's happening to the neutrinos. They're just coming along for the ride. Their entropy is conserved trivially because they're just like not doing anything. What's happening to the electrons and positrons and the photons, that's all in equilibrium. That's not out of equilibrium physics. So the key part of this process never involves some non-equilibrium process.
But I guess what's confusing me is if the neutrinos decouple over some finite length of time.
But during that decoupling, their temperature never changes away from the temperature of the photon. So during that process, why?
They couple other stuff.
Because during that time, everything's going like 1 over A. So it's just like the key of equilibrium is to keep them in equilibrium when stuff happens, but basically nothing interesting is happening at that specific moment, except that they're not. So you take two things that are in equilibrium and they just become two separate things that are themselves in equilibrium, but there's no important non-equilibrium effects that talk between the two sectors because they just fall apart. So I started with one thing in equilibrium and I made two things that are in equilibrium with themselves, and that was the only important thing that happened. But that process of splitting from 1 into 2 didn't violate equilibrium of the individual pieces. So I'm just applying equilibrium sort of piece by piece. But I mean, again, if you can go and check, this is an approximate argument anyway. So it is actually true that this is not 100% accurate, and we'll talk about the corrections that come in. But it's an implicit assumption, let's say, that nothing important non-equilibrium happens during that decoupling. But I'll explain the non-equilibrium things that do happen in a second. Okay, so we can now take this and do the following. We have a T nu on this side because the temperature of the photons and neutrinos were exactly the same at the earlier time, and they're were exactly the same at the earlier time, and now we have the temperature of the photons over here on the right-hand side. Now, because T nu is a constant, I can replace this with either T nu, so originally this was T nu at time T1, but it's also the same as T nu at times T2 times A at T2. So I can replace this so the factors of A go away because that's a constant. And what we're left with is, here, let's switch these boards. So, and what we'll be left with is that the ratio, so we solve this, we get the ratio of temperatures of the neutrinos to the ratio of the temperature of photons cubed is equal to the number of degrees of freedom in photons divided by the number of degrees in protons plus the number of degrees of times 7/8 times the number of degrees of freedom in electrons plus the number of degrees of freedom in positrons. Okay? And now we just have to plug in numbers. So there's 2 helicities of photons. There's 2 helicities of electrons and positrons. So every number here is 2. That makes this 4. That makes this 7 over 2. You add 2 to 7 over 2, you get 11 over 2. You have 2 upstairs, and that gives you 4 left. Okay? This is a very, I don't know, you'll see this factor floating around if you read enough cosmology papers, and that's where it comes from. Okay, so the ratio of the neutrino temperature to photons cubed is 4/11, and this tells us that today the neutrino temperature is about 1.9 Kelvin. So there's a thermal distribution of neutrinos in the universe. They're slightly colder, but not that much colder than the photons. In fact, it's an important thing for our later discussion that if you convert this into how much energy was carried by neutrinos in the early universe, neutrinos are approximately 41% of the total energy during radiation domination. So this 4/11 is a suppression, but it's not very much of a suppression. And so that's why actually neutrinos are a huge amount of energy density. That means that any gravitational effect, which is what we're going to talk about later, that involves the radiation is going to get 41% of its contribution from the neutrinos. So it's not like some tiny effect we're going to be looking for in the CMB. It's a huge factor in any gravitational effect is going to get a huge contribution from the neutrinos. Yeah.
How would the presence of a heavy right-handed neutrino change this story?
How heavy?
You tell me.
Well, if it's like, so if it's sub-EV, then it will basically be like anything else if it was thermally produced. The couplings of neutrinos are complicated and mass dependent. So if it's thermalized, then it doesn't change. Like if it's thermalized, it will follow from what we're going to do in a second when we add extra particles. So we'll talk about extra particles in a second. So the key thing here is that I use the decoupling at around an MeV. So the key temperature is an MeV, and that depended on how neutrinos couple with Standard Model. Other questions? Okay, so it's conventional to instead, so energy density in neutrinos, that's the thing that we're gonna look for. Here, I'll go to the other, I'll use the other board. It's getting lonely. So the energy density is what we measure, right? So gravity cares about the energy density in neutrinos, and so, and not its temperature directly. It's conventional to write the energy density in a funny way, which is to write that the energy density in radiation is equal to the energy density in photons times 1 plus, let's see if I can get this all right in real time, 11 forced to the 4/3 times a quantity called N effective, okay? This is just rho plus rho neutrino. Now, this definition has been made so that in this, when this calculation is accurate, N effective would be equal to 3, right? So this is the temperature to the 4th. This is the 7/8 factor. This is the number of generations of neutrinos, 3. Or I think it's supposed to be 7/4. Sorry, it's supposed to be 7/4 because there's 2 spins for each neutrino. Yep.
Even without BSM physics, though, you can shift N effective away from 3 via incomplete decoupling, right?
Yeah. So this is when our calculation holds, and so there's actually 2 important effects that mean the true value in the Standard Model is 3.045. This is the best measurement estimate of the Standard Model value. The error right now is in the 4th decimal place. Okay, so we did this calculation, and hopefully this will address the question, which is the 3 assumed 2 key things. So the 2 key assumptions that are broken here are, so the first was decoupling, and that the entropy is basically a dilute gas for the entropy, okay? So both of these things are broken by small amounts that give you this 1% correction. The incomplete decoupling is because there's some finite branching ratio back to the neutrinos. This part is less obvious. This is QED. There's like some QED plasma effects that mean that the G star of the Standard Model is not quite just counting spin degrees of freedom, but there's like some binding energies in there that come from QED. There's also a bunch of stuff to do with neutrino mass oscillations and stuff that I can't remember how big an effect is, also shows up in here. But these are the 2 big ones that explain why this number is not 3.0, but something like 1% bigger. Okay, so this is the Standard Model value. Now we get to dark radiation, which is, okay, what would happen if we had extra light particles that went through a similar story? Okay, so we're going to call these things light relics. So light relics is just shorthand for a particle with mass that's, let's say, much less than an eV and was in thermal equilibrium. So I'll just use that as a generic term. The reason this is sufficient is because if it was in equilibrium, then we know that at some point it was relativistic. It's pretty hot. Because the mass is very small, given what we know about the temperature, which we'll talk about in a second, it will basically be relativistic at the time of the recombination, so it will look like radiation. This is a sufficient set of assumptions to make that work. Yep.
What time are we conventionally measuring an effective mass?
So okay, that's an excellent question. This is for the purposes of the CMB. So this is for the purposes of the CMB. If we were using BBN, which you can also use to define an effective, then this mass can be bigger because it will still be relativistic at BBN, which is about an MeV. So, however, we'll talk about things that are in that window and what happens to the CMB measurement when something is light during BBN but heavy during the CMB. Or it goes away during the CMB is probably a more accurate way to say it. Now, for the later universe large-scale structure, the fact that this mass is non-zero will show up in the form of how we measure neutrino mass, which is next lecture if we get there. Okay, so this is sufficient for the purposes of CMB, not sufficient for the purpose of large-scale structure. The mass matters in large-scale structure, even if it's sub-eV. Okay, so let's imagine, we'll just call it phi. There's some particle phi that satisfies these conditions, and it couples to the standard model through some operators, and we'll give it a dimension. So the dimension of these operators is delta is equal to 4 plus n. N will probably be an integer for our purposes, but there's no reason, like in some strongly coupled thing, it couldn't be something non-integer, but I've called it n because it's mostly integer in the case that we care about. Okay, so again, we just write down some effective operator that allows phi in the standard model to come into equilibrium. So there's some production rate that, again, we can just put in the units. It goes like the scale, this capital lambda to the 2n. So because it's a rate, it must go t to the 2n plus 1. We're going to compare that to Hubble, which again was t squared over m Planck. And so that tells us that the freeze-out temperature goes like lambda to the 2n, lambda to the 2, t freeze-out to the 2n minus 1 goes like lambda, this squared scale, lambda over to the 2n divided by m Planck. So this temperature, this scale is usually pretty high, but it's below the scale where this effective operator applies. Also, for n greater than a half, the thermalization happens at high temperatures. This term wins at high temperatures. This term wins at low temperatures. So as long as this is any kind of irrelevant operator, this picture that looks like the neutrinos will hold, but the decoupling temperature is now arbitrary. The decoupling temperature is set by this scale. So our knowledge of the scale at which it freezes out is a direct reflection of the coupling strength of this new particle. Okay, does that dimensional analysis make sense to people? Okay, so assuming that this scale is less than the reheating temperature, so let's make this assumption. Then we know that this particle was thermalized. Phi was definitely thermalized in the early universe, assuming that this temperature of freeze-out is high enough. So basically meaning the temperatures of the universe were bigger than the temperature where it decoupled. So at some point it was in equilibrium, and it falls out of equilibrium at T freeze-out. Okay, so now we can go through a very similar argument to find out what the contribution to N effective is. So to determine the correction to N effective, we can just figure out what the temperature of the, we can just determine the temperature of phi relative to the temperature of the neutrinos. Okay, so we'll play the same game, but now we're going to go back to this T freeze out, which we're going to assume is much before neutrinos decouple. So let's assume that T freeze out is much greater than 1 MeV. And so what we'll have is that the entropy at the temperature where it freezes out is given by whatever the number of degrees of freedom in this phi sector are, plus G star of the standard model at the temperature TF, times TF A of TF cubed. And we're going to equate this to, let's say, the entropy of the universe at 1 MeV, or let's say 10 MeV before neutrinos decouple. Okay, so in that case, we have, again, so this thing decouples, it goes through the same story, its temperature redshifts like 1 over A, so the entropy in this sector doesn't change, it's just the same as it always was. And now we have the temperature of the neutrinos times A cubed. It's the neutrinos that are going to get heated up in this case, times the number of degrees of freedom in photons plus 7/8 number of degrees of freedom in neutrinos plus electrons plus positrons. Okay, now I'll just write the final formula so you can see it. So that tells us that the ratio of the temperature of phi to the ratio of the temperature of mu cubed is, if we do this math, I believe it's 43 over 4 for this thing here, divided by the G star of the standard model at freeze out. Okay, I'll raise this so you can all see it. Oops. Okay, does that make sense to people? Yeah.
For your calculation of entropy at 10 MeV, why do you have T freeze out in there?
Oh, so because this is the entropy, this is the entropy when it froze out. This is the entropy at 10 MeV, and it's the ratio of those two. This is the G star from just the standard model before neutrinos decouple. This is the G star of the standard model at the freeze out temperature.
I'm confused about the line above. The G phi T freeze out times A of T freeze out cubed.
Yeah, so that's a G star of T freeze out is some function. And does that, like, it's not I'm not multiplying, it's a function. Like, I'll show you what the function looks like. Does that do you know what I mean?
Still, I would guess that you want to put 10 MeV in there for your temperature.
No, so this is the entropy at T freeze out. The top line is the temperature at T freeze out, and G star is the number of degrees of freedom of the standard model at that same temperature.
Yes, it's the next line.
It's the next line, okay. So this is G phi. Here I've used the fact that the temperature of this phi doesn't change. It goes like 1 over A.
Oh,
so I've skipped that step where I replaced this at 10 MeV with the same quantity earlier.
Understood, thank you.
Sorry, why are you relating it to 10 MeV? I missed this.
Oh, this is just before the neutrinos decouple. So I can just, if I calculate the neutrino temperature, the ratio to the neutrino temperature, then I can determine N effective. Yep.
Okay, so just you were at the 4 over 11 factor. So what is part of this? Is this number very precise, or there's
for the corrections we're going to talk, well, even the 3.04 does not need to be as precise for experiments. I'll talk about experiments in a second. This is good enough for experiments for the BSM physics you'll care about, right? Because if we put a 1% correction to this, like that's a 1% correction of a number we haven't detected yet. So this itself will be 1%, and the error will be 10 to the minus 4.
So that depends on if you have some BSM particles that contribute maybe
Oh, okay, so if BSM particles contribute to G star, then we have to care about that. But we'll talk about that in a second when I show you the results. Any other questions? Was that a question over there? Okay. Okay, so so this tells us that basically there's a correction to N effective that's proportional to this ratio to the 4/3 power. Because this is the temperature, so the correction, this is the ratio of the entropies, basically, of these two sectors. So if I go to the 4/3 power, that's a correction to the energy density. So what we'll get is we'll get a correction to N effective that's proportional just to this combination, 43/4 divided by G star of F of TF to the 4/3 power, and then times the number of internal degrees of freedom of the phi sector. Okay? So the key fact here is that this correction is a universal function of two quantities. There's an overall multiplicative constant, which is how many degrees of freedom are there in this phi sector. And then there's this function, G star, that we have to calculate. This is a hard thing to calculate, but in principle, once I know this, I know delta N effective for any particle satisfying the set of assumptions that I was led here with. So because of that, you get this kind of universal curve. So I'm going to plot T freeze out, delta N effective. Okay, and I'll use some colored chalk. Okay, so I'm going to draw a line here. This is about 100 MeV. Now we'll do, okay, so this one here will go something like this. And then there'll be, here I'll even use yellow for slightly higher. Okay, so there's going to be a bunch of lines that basically follow this same pattern multiplied by each other, okay? So importantly, this is an asymptote that goes to 0.027 times, these things are, so this red one here is for G phi equals to 1. Well, I've just drawn, let's say G phi is equal to 7/4 for like a Weyl fermion. And then they stack up just on top of each other by multiplying by how many degrees of freedom there are. So why are there asymptotes? Why do these things go to a constant? So here I'll put this suggestive energy scale somewhere here. How many degrees of freedom in the standard model that are heavier than the top mass? Okay, maybe I should have plotted G star of F. So G star of F, remember, is all the degrees of freedom in the standard model, right? So G star of F is equal to the number of relativistic species in bosons at temperature T plus 7/8 the number of fermionic degrees of freedom at temperature TF for the standard model, for standard model particles. Okay? So if I'm at 10 TeV, does it matter if does this number change if I go to 100 TeV? Why not? Correct. So this thing asymptotes. So for T much greater than T, the top mass, this quantity asymptotes to 106.75. Okay, so the fact that there's not a huge number of degrees of freedom right above the top tells us that this thing asymptotes. Now, if you still like weak scale SUSY, then that's a big thing. If you just have a few particles, like a WIMP or something, it doesn't particularly matter if this changes by an order 1 number. The key thing for our prediction is just that this number is about 100 and not 1,000. So that's what's happening here, is we're just hitting the asymptote. There's no more degrees of freedom. There's only so many degrees of freedom that it can annihilate back to photons in order to dilute the energy density that's being carried by our new particle. So it sets this really interesting number 1% change to N effective that is independent of the temperature of freeze out. So here, if we can detect down to this line, then we can detect anything that was ever in thermal equilibrium, all the way to the reheating temperature. Now, the reality is that the next generation of experiments are going to get to exclude about here. So this is about 100 GeV. So this is CMBS4. We'll get to about this level. So they'll exclude sigma N effect. They'll exclude delta N effective less than 0.06 at 95% confidence. So we're getting to the point where we're measuring some of these asymptotes, like for a handful of degrees of freedom, and getting freeze-out temperatures that are at the weak scale. Meanwhile, Planck is somewhere up here. This is about 0.3, which is where Planck is at 95%. Okay, what's happening in this line here? Why did I put this region? It should be a little region here. Was that? Yeah, so this is the QCD phase transition here. So there's two important features of this plot. That is very flat out here, which means that tiny improvements in N effective can translate into huge improvements in the reach in terms of T freeze out. This is the opposite. We're going to have to burn through a lot of experiments to get from a very small change in temperature because so many degrees of freedom in the standard model annihilate during the QCD phase transition. So that's kind of the overall character of this plot. There's a bunch of details. This plot comes from doing lattice calculations in equilibrium to determine the entropy of the plasma as a function of temperature. Okay, but this is the kind of key takeaway from the sort of fundamental physics point of view, that in a very general sense, we can search for new light particles using N effective. And since we're going to use the gravitational influence of these particles, the only thing that matters is that they were in equilibrium. The details after that don't really affect our ability to search for them. Okay, are there questions? Okay, how am I doing on time? Okay, I got 10 minutes, is that right? Okay. All right, so this is what we want to look for. Now the question is, how do we look for it? Okay, so the key is we're looking for the influence of this extra radiation on the cosmic microwave background. So there's kind of two things. I'll probably only get to do the first part. So the first thing we're going to talk about is called diffusion damping. This is what I was talking about earlier in the lecture. This is the fact that the power spectrum goes down at high L because sound waves dissipate. Okay, so that's the first thing we're going to look for. Now, this is going to be sensitive just to the homogeneous energy density. So this is going to be related to the fact that the expansion rate during radiation domination is going to be driven by the photons and the neutrinos together. So we're not going to worry, but for this effect, the main thing that matters is the change to Hubble because of the way in which having more radiation increases the expansion rate of the universe. So that's not to do with perturbations of the neutrinos. This is the part that will be more will be less important in terms of like the detailed properties of neutrinos. We'll talk about the perturbations probably next lecture. Okay, so to understand the influence of this, the key thing is just to remember that H, the units of H are 1 over time. Okay? That's more or less the main effect. Okay? So what we have to worry about is that Hubble controls the time scale on which things happen in cosmology. Now, in detail, the way that we see this is usually to work in terms of conformal time. So we're going to work in terms, so if we work in terms of conformal time, we're going to call that tau. That's usually equal to, so it's usually defined like this. The conformal time is defined by ordinary time divided by A of t, or that A of t times d tau is equal to dt. But we can integrate this expression on both sides. And then, of course, you can rewrite this as an integral a over h times a squared. So here I just use that. Okay, so that's just a change of variables. Okay, it's convenient because with things like t, we have to worry about units, a are dimensionless, and so we've seen, as argued here, that all the units of time are just going to be packaged into this the expansion rate. Okay, so I'm starting here because the conformal time is the right way to describe the sound waves. So remember, we were talking about sound waves as if they lived in flat space, but of course, it's kind of like a WKB approximation. Their wavelengths are kind of being slowly stretched by the expansion of the universe. But we can actually describe them in conformal time in exactly the way they would look like waves, so that they basically just look like a WKB solution. So in an expanding universe, our density fluctuations of neutrinos, or of photons, was just given by this. Okay, so it's k, cs times k, and then it's a factor of conformal time. So this is to account for expansion of the universe. Okay, so this then turns into our picture where we related k was equal to L divided by the distance to the last scattering surface, which I can write in conformal time this way. So conformal time is nice because in conformal time, light moves along 45-degree angles. In this description, this is the relationship between our Fourier mode and our spherical harmonic. So this tells us then that the peaks in L are related to, so if I translate, that means that the CLs are approximately cosine squared CS L times tau of recombination divided by tau today minus tau at recombination. And this piece here is approximately the tau today. So the conformal time today is much bigger than the conformal time at recombination. So it's dominated just by what the conformal time today is. So because of that, this is a unit of time. If we change the Hubble expansion rate here, it moves the locations of the acoustic peaks. So roughly speaking, the peak locations are set by the zeros, or sorry, the maxima and minima, or just the maxima of the cosine squared, or the maxima minima cosine. So that is when we get this combination, CS peak divided by tau naught is equal to some integer times pi. Or said differently, that the peak locations are equal to n times pi times the conformal time divided by CS times the conformal time at recombination. Now the problem is that these things are fixed by observations. So again, this is a unit of time. Hubble will enter this expression, but we actually don't want, this will move the peak locations, but we go and measure the peak locations. We know where they are. So these things are known. So the biggest effect of neutrinos is to move all the peak locations. But our data has already determined where they are. So we're not allowed to just freely change expansion at recombination, holding the expansion today fixed. So instead what we do is that you can think of this as being like a ratio of Hubble expansion at recombination divided by Hubble today, which just sets the units of the conformal time today. So what we want to do is not to change the amount of expansion to, at recombination, holding Hubble fixed today. We want to change them together so the peak locations don't move. Okay, so we have to be careful that from the purposes of data, we always change H at T star and H naught together. Okay, so that's the key thing that's going to affect how we look for the actual observable effect. If you didn't do this, you would get the exact wrong behavior. And so we'll talk about that next time. But the key thing is that this fact that we know where the peak locations are mixes what we know about the universe at the time of recombination and what we know about the universe at low redshifts, even though the neutrinos are totally gone today and don't directly affect the expansion rate of the universe. But we have to change that if we want to keep the CMB unchanged. Okay, so we'll pick up from there tomorrow.
Yeah, I definitely have a couple questions.
Okay.
So this, I got a little bit lost what was happening here. So I guess from where it seems like right now, it seems like we're trying to constrain when this phi would decouple at some high temperature. But this looks like it's only sensitive to recombination today.
So once it decouples, like it has some, so at the time when it's in thermal equilibrium, there's the same number of phi particles as there are photons. So there's a ton of them. Now, they get diluted, but they get diluted at most by like 1% to 1% of them. So they're still around in some large number, just not as much as the photons. So we can't get rid of them. We're stuck with them once they're out of equilibrium.
I see.
And so now we're just,
Recombination comes around.
they're still there. They're still there,
Okay.
exactly. They're just like a neutrino. They're stuck, we're stuck with them, we can't get rid of them, they're there, and so they affect the expansion of the universe.
I see. I see. Okay. I have more questions about all that.
Yeah, no problem.
So one application is actually, this H naught is a measurement from CMB. Actually, we have some mismatch between.
So this is, I mean, this is just a parameter, right? How we measure H naught is a totally different story. I'm just saying that for the purpose of the CMB data, when we change an effective, we're going to change H naught. So a higher N effective always corresponds to a higher H naught than if N effective was the same as the number of neutrinos. So you always have to change them together. Like that, but that's just a fact about where the data gets it. So like, this would say like when you have the curves, right? So if you measure N effective and H naught with the data, it will always take a contour that looks something like this. Like, and the fact that it's at some angle, that doesn't care about where this thing is centered. This is just a fact about this is a fact that we measure peaks really well. Does that make sense?
So by measuring this, so we know this peak. This determines this rate by just doing this.
So we can keep the peak locations fixed if we make this combination. We change these things together.
Then we end up with this.
Yeah. Yes. But then the reason that this isn't a line is because of the effects we're going to talk about later. So this is the biggest effect, but it's the one we don't want to be there. So because this effect is like not, we definitely see the peaks don't change. So we have to live somewhere on this line. And then the edges of this are going to be set by diffusion.
So to determine this H naught, we need another.
So there'll be a second effect, which is smaller than this effect, that is actually how we measure it. So it's just the easier way to think about the data is that we hold this fixed, and then we look at what other things happen with the CMB. And those other effects are the ones that dominate the constraint.
That's why people, to reserve some tension, over tension, increase this delta to match the supernova.
So the supernova is in tension with this measurement. So if I added supernova data, it would just be up here, and it's just inconsistent. So I'm intentionally not talking about the supernova data.
Actually, that was my question. So we have tension between these two H naughts.
Yes.
In this H naught, you mean only this CMB.
Well, for now, I'm assuming there's no contradiction. It's the same H naught, but there is a tension with supernovae, and you can probably guess my opinion of the supernovae. But yes, but yes, it's the H naught of the late time expansion. However you choose to measure it.
Okay, so let's say that we're post-neutrino decoupling. We have like a light sterile neutrino, but the sterile sector is initially unpopulated, and then we want to populate it using this like the collision-driven production mechanism. It's like I forget what it's called exactly.
Okay, so
but
you want to populate neutrinos. Some other particle that happens to be a fermion, we'll call it a sterile neutrino. You're going to
Yes.
populate that after the original neutrinos have decoupled.
yes, we
Okay.
have some sort of mechanism,
Yes,
some sort of
correct.
subtraction or something to suppress the mixing to the point where we can
Yes,
keep it
correct.
unpopulated to this point. Would that change ineffective once we do?
Yes, correct. So it will. So coupling. Okay, so it depends.
I'm just wondering because, okay, we have this, the question is energy conserved or is entropy conserved?
Entropy is
We have
conserved,
this-
not energy. So
But
one.
this is a non-thermal production mechanism, no?
Okay, so if it's in equilibrium, then entropy is conserved. Okay, so you're going to say so nothing is happening in the neutrinos. We'll start that. Okay,
Yeah.
and so whether entropy or energy is conserved is going to affect things at the factor of 2 level or like order 1 numbers, but just intuitively,
Yeah.
what's going to happen unaffected? You had energies in photons. You're taking that energy in the standard model. I assume you're taking it out of the standard model. You're taking
Yeah,
the standard model, you're turning it into sterile neutrinos. Okay, so the energy in the photons had to go down, right? So like we took energy out of the photons. Now if we
But
did it,
the neutrinos are decoupled at this point.
yeah, the neutrinos are coming along. Like so, but like the neutrino. So what does that mean for the neutrinos, right?
Okay.
We definitely measure the CMB. Like at the end of the day, so like the temperature of the photons.